Welcome to video 4 of section 5, Recurrent Networks, Training a Sentiment Analysis Model for Text. In the last video, we saw the main difference between convolutional and recurrent layers. Here, we will talk about sentiment analysis and training our recurrent neural network with Keras. So what we mean by sentiment analysis? Remember our pictures of cats and dogs? Let's say now that we are in a photography contest, and we submit each image for an open jury where anyone can come and describe what he thinks about the image. The question is, how do we know if a reaction was positive or negative? Let's read some reviews and see that just catching keywords isn't enough. For the first one on the left, funny picture, but the cat looks scared and I think you got his bad angle. The other one is, too bad, I can't see from here and look at his eyes all day. Such a well-crafted, profound, and reflexive picture. See how we have positive words in the negative review and negative words in the positive one? It all depends on understanding the entire phrase context, right? The dataset we are going to use to learn this task is the IMDb movie review dataset. Here, we move to our IPython notebook to do some coding. We will use part of the IMDb dataset that ships with Keras. This way, you can go to Keras example folder and check out different ways of solving this problem. So in this first cell, we load Keras, Theano, and everything that we need. Pay special attention to this line. Here we import the IMDb dataset from Keras datasets. In this other cell, we have a few hyperparameters that we are setting up. For instance, the maximum number of features, the maximum length of each phrase, and the number of phrases that our model reads at a time. The IMDb dataset can be loaded like this. This cell has some extra preprocessing on the text sequences. Here, we pad the sequences so that they have all the same size and can be processed in parallel. But inside Keras code, padding values don't contribute to the dynamics of the recurrent neural network. It effectively just skips the padded values. Just for curiosity, here are a few samples from the IMDb movie review dataset. A negative review, for instance, is this one. Even those from the era should be turned off. And a positive one is, I didn't know this came from Canada, but it's very good, very good. You know how considerate this person is being to Canada here though. We can print a row from our X trained data to see how these phrases look like in the input of the neural network. They are essentially just the IDs of each word. And this is a common practice in natural language processing, to encode each word as a scalar, but note that this doesn't account for relationship between words. So inside our model, we have to learn better word-to-vector representations. And here's how we build our recurrent neural network with Keras. As always, we start by defining a sequential model. Then we add our first layer, embedding. And this is the one responsible for doing a one-to-one mapping between word IDs and vectors. The vectors here have 128 dimensions and are adapted like any other neural network parameter. For a small dataset, like the one you're using here, this might not be a good choice. It would be better to use pre-trained word-to-vector representations, such as Google's Word2Vec or Stanford's Glove. You can find a Python implementation for Google's Word2Vec in Gensim repository on GitHub. Gensim is really well written, well documented, and has a simple to use Python API. Glove from the Stanford NLP group is also a similar model for doing word-to-vector representations. I recommend you to read more about word-to-vector representations. It is really interesting. Back to our IPython notebook. The next layer that we add to our model is an LSTM layer. The LSTM receives a sequence of 128 dimension vectors coming from the word embedding layer, and it outputs a single 128 dimension vector that is exactly its last hidden state, right after it finishes reading the entire input sequence. Finally, we apply some dropout and one last projection. We use the sigmoid activation function to make sure that the final output of the model is bounded between 0 and 1, using 0 for negative reveals and 1 for positive. we compile with model.compile. After compiling the model, I compile another function, but this one just to get the outputs from the embedding layer, which is the first one from the model. And we can verify what the outputs of this layer look like. So here we have an input, which is just our regular string of integers. We have 100 of them. And here's how the embedding vectors look like. For each one of the integers, we have a vector of 128 dimensions. In these lines of code, we will train our model. Can you see the differences from the way that we trained our convolutional neural networks in the previous videos to the way that we train our recurrent neural networks here? No? That is because there is no difference. Theano and Keras handle everything, all the data, and the backpropagation through time. They do all that for us seamlessly. This way, we can focus in designing the appropriate architectures for our problems. So let's just run this. After we are done training our recurrent neural network, we get almost 82% accuracy on the held-out test set. To see how to write models that get even better results, go to Keras examples folder and see the models that have IMDb on their name. In this section, we focused on recurrent layers, its comparison to other types of layers such as convolutional, and which role recurrent layers play in deep learning applications. We concluded this section training our recurrent neural network with Keras. In the next section, we have a bonus for you, an awesome challenge that will put your deep learning skills into test. Can you do automatic image captioning with deep neural networks? Also, in this next section, we'll have a little video with some details about TensorFlow.